We're going to introduce a few important families of discrete random variables, right? And the way to think about this is that many problems that we care about in engineering and beyond have the same underlying probability structure. So even though the description of the problem in words and the context might be quite different, the math underneath is exactly the same, right? And because of that, it's useful for us to learn a few families of random variables that show up quite often, and that'll help us avoid repetitive calculations. And in fact, we don't even need to do these calculations. So what this is going to enable us to do is to skip the calculations of things like means and variances and just look them up. So you don't even have to memorize these. You just need to recognize when these families have occurred and remember where to look up those values. And here we're just going to introduce a handful of random variables that are really useful, but you'll find hundreds of these families online and in other probability and statistics textbooks. So most of the time when you have a problem that looks like it has a nice structure, you can usually just go and look up what the things like expected value, variance, and other quantities might be. Okay, well, let's start with something really simple just to warm up. And this is going to be the foundation of some of the other things we learned. So what I'm going to do is I'm going to introduce each random variable, tell you its name, give us the notation and the parameters, plot the PMF, tell you the range, mean, variance, interpret it, and then finally give you a few possible applications out of the many, many applications that are out there. Okay, first is Bernoulli. So X is a Bernoulli P random variable if its PMF is 1 minus P for X equals 0 and P for X equals 1. So that just looks like 1 minus P at 0 and P equals P at X equals 1. Okay, so really simple. And the range here is really just 0 and 1. The mean is just P, because it's 0 times 1 minus P, that's just 0, plus 1 times P, that's P. The variance you can also work out by hand. It's going to be P times 1 minus P. Okay, and the interpretation of this is quite simple. It's just a single binary trial, and the probability that you succeed is P, all right? So just think there are two outcomes, win and lose. Win has probability P, and we map win to 1 and lose to 0. What are some engineering applications for this idea? Well, you could think that success is that a packet is received, or that a treatment is effective, or that you are manufacturing a part which is quite difficult to make, and this time it's within your desired tolerances. Okay, the next random variable we're going to introduce is geometric. So X is geometric P if it has PMF that looks like the following. It's basically a geometric series, and it's decaying like this. So you start with P, and then you multiply by 1 minus P to the X minus 1. And X takes values in 1, 2, 3, 4, 5, and so on. So the PMF looks like this decaying series, right? So here I start at P, and I just keep going down, multiplying by 1 minus P each time. The range just from this is going to be 1, 2, 3, and so on. The mean turns out is 1 over P. Okay, and that actually requires a little bit of work to show. We're not going to do that here. You can just take for granted whenever you need it that the mean is 1 over P. The variance similarly is going to be 1 minus P over P squared. A little bit of work and just working with an infinite series to figure that out. You don't need to do that. What's the interpretation? Well, you can stare at this formula and convince yourself that it's the number of Bernoulli P trials that you need to do until your first success, right? So what's going on is that, let's say you fail 4 times, and on the 5th time you succeed. So each failure has probability 1 minus P, and they're independent, so you're multiplying them 4 times together. And on the 5th time you succeed, that has probability P. So since the 5th one was success, then you need 4, or that's what this X minus 1 is. So you need 4 failure probabilities multiplied together. So that's where this is coming from. Again, you don't need to derive it from scratch. You just need to know that that's when you would use it. So some applications would be the number of packet retransmissions you need until the router successfully acknowledges that it got the packet. It's the number of patients you would try an experimental drug on until you found the first patient that was cured. Or it could be the parts that you manufacture until you get the first part within your specifications. Okay, those are just a few applications. All right, related is the binomial random variable. So x is a binomial NP random variable. So it has two parameters, n and p, if the PMF is the following. So it's n choose x, p to the x, 1 minus p to the n minus x, and it takes values from 0, 1 up to n. All right, and so the PMF kind of looks like this. So it starts out at 0, and it goes up, and then it's centered somewhere, and then it comes back down to n. And the reason I didn't draw in the center here is that depending on whether n is odd or even, you might have 2 points of equal height in the middle, or one highest point in the middle. So it just depends on whether n is odd or even. The range is just going to be 0, 1 up to n. The mean turns out to just be n times p. And let's think about this for a second. So this is just n times the mean of a Bernoulli random variable. What's the variance? Just n times p times 1 minus p. That's just n times the variance of a Bernoulli random variable. So that's a nice coincidence, but it turns out not to be a coincidence. It turns out the right interpretation of this, it's the number of successes that you see in n independent Bernoulli p trials, right? So you're trying some game or some process n times. Each time you might win or succeed with probability p, and you're just counting how many times you succeed in the end. So it makes sense that the average number is going to be n times your probability of success. And variance kind of follows from the same idea. We'll see more about why that's true a lot later in the course. The PMF, the one thing I want you to notice here is that the n choose x is counting the number of ways that your x wins or successes are positioned out of the n possible positions. Some applications, you could think that this is the number of packets successfully received out of n transmitted. Or in a trial, so a trial with n patients, how many were cured by the drug that you tried? Or how many parts do you manufacture within tolerance? Let's say you try to make 100, how many of them actually were made successfully? Another random variable that we'll introduce, which seems like we might not need formal definitions for it, but it's still useful to have around, is this idea of a discrete uniform AB random variable. Okay, so all this means is that I have equal probability starting from x equals a going to x equals b, okay? And in order to have equal probability, each probability needs to be 1 over b minus a plus 1, because if you count, there are b minus a plus 1 possible values, right? So the PMF here will just look like equal height in the range where it's defined. It could be, it could have negative values, it could have positive values. It's up to you. So the range, as I said, it starts at A, it goes up to B. What's the mean going to be? Well, intuitively, it should be A plus B over 2, and that's exactly what it is. So why do we define this random variable? Well, one reason is that the variance is kind of annoying to work out. You could do it, but here's a nice formula you can just use to simplify some of your work. So it's b minus a times b minus a plus 2 over 12, which is b minus a plus 1 squared minus 1 over 12. The interpretation is really just that the outcomes are equally likely to take values between A and B. And just to keep this short, I'm just going to give you one simple application we've seen before. You roll a die, it's between 1 and 6. Okay, and so then you could get the mean and variance of those values from here. Our final random variable is going to be a Poisson random variable. So x is Poisson alpha if it has the following PMF. So it's going to be lambda to the x over x factorial e to the minus lambda. And it starts from 0 and just keeps going up. All right, so it has a shape that kind of looks like this. So it goes up for a little while, and then it kind of comes back down. All right, the range is 0, 1, 2, and so on. The mean is simple, just lambda. Variance, also simple, just lambda. Calculating that is a little bit more work. Okay, and this formula might look a little complicated, but it's a very important fundamental idea in probability. We're not going to get into deriving why this is true and how it's related to the other random variables, but it is. And the way to think about it, it's the number of occurrences of a process in a fixed time window. Okay, so if you have something that you consider, let's say, kind of rare or happening kind of sparsely, and you want to count how many times it happens within some block of time, Poisson might be a good way of modeling that, right? So as an application, you could think about the number of photons hitting a CCD pixel in a digital camera in 1 millisecond, or the number of neuron action potentials you observe in 10 seconds of recording, or the number of turbines, let's say wind turbines, that fail in 1 week. Okay, so these are different things you could think about happening in a fixed time window. Okay, to wrap this up, we're going to work out a long example. Okay, so our example, we're going to say that we have a favorite sports team, maybe it's even esports, and our model is that they win with probability 3/4 independently of other matches that they're playing. So if you're watching a match, the probability that they're going to win, regardless of whether they won or lost before, is 3/4. Okay, and let's let X be the number of matches that I'm watching before I see a win, or until I see a win, including that match. All right, so what kind of random variable is X? It turns out it's geometric 3/4. Okay, and the first thing I want to say here is when you're naming a random variable, don't forget to include the parameters. So in this case, it's fine to say it's geometric, but I should also say it's geometric 3/4 because that 3/4 is telling me the probability of winning, and it's the value I need in order to actually draw the PMF and work out the mean and variance, etc. So why does this make sense? Because it's basically Bernoulli trial. So, I'm trying to see a win. I'm just trying to see how many times do I need to try before I see my first win. That's exactly what X is, and that's exactly what a geometric random variable does. Okay, so the next question is naturally, how many matches do I need to watch until, on average, I see a win? Okay, so let's say every day I sit down to watch a few games, and I'm going to wait to see how long I watch to see a win. On average, I'm going to wait 1 minus p, which is 1/3/4, or 4/3 matches, right? So that's how long I need to wait on average. So they usually win. So 3/4 is a pretty high win probability, but still maybe I need to watch more than one game. It's possible to watch a lot of games if they fail many times in a row. And the average is going to be 4/3. Okay, what's the probability that the first win that I see, all right, so I'm looking at this random variable X, what's the probability that the first win only occurs on the third match or later? Okay, so the first 2 games are losses. So that's the probability that X is greater than or equal to 3. So the first thing I had to do was translate this statement in words into a mathematical statement. So the first one occurring on third or later is just the event that X is greater than or equal to 3. And I know that I can just add up the PMF values from 3 up to infinity. It really goes up to infinity because the geometric random variable goes on forever. And now I know the PMF of the geometric random variable. I can look up that it's p times 1 minus p to the x minus 1. So I can look that up in my definition. And so I end up with this infinite series. Okay, and technically I could work out the value of this infinite series. Okay, so it's possible, it's a geometric series. I could look that up and I could do this calculation. But a lot of the work that we're trying to do in this course is to find ways to get the answers that we want without doing the tedious calculations. And this one is already too tedious for us. So what's a way around doing this much work? Well, instead of calculating all of the values from 3 on to infinity and adding them up, I could just take the complement. So I could take 1 minus the probability of x greater than or equal to 3 complement, which is just the event that x is less than 3, right? So if we look at x greater than or equal to 3 and x less than 3, you can see their complements, so the complement property can be applied. And now I'm going to work out that this actually means that x is less than or equal to 2, and the reason for that is that in this particular example, x only takes values on its range 1, 2, 3, and so on, right? So this actually is going to be 1 minus the PMF value of x at 1 plus the PMF at 2. That's 1 minus 3/4 times 1/4 to the 0 plus 3/4 times 1/4 to the 1. So 1 minus 3/4 minus 3/16 is 1/16. Okay, and if you did go and calculate that geometric series, you would get the same answer. Let's change what we're interested in a little bit. Let's say I count the number of wins that I see in 6 matches. So I watch exactly 6 matches. How many wins are there? Well, this is one of those random variables that we saw before. What kind is it? Well, it's the total number of wins in a fixed number of matches, and that's going to be binomial 6 3/4 because there are n equals 6 matches and 3/4 was the win probability. And again, I need to write 6 and 3/4 in order to fully describe this random variable. I don't want to forget that. Okay, and let's say I'm interested in knowing the variance of y. And I'm also interested in knowing the second moment, e of y squared. Well, the variance, I have the formula. From before, it was n times p times 1 minus p. So that's 6 times 3/4 times 1/4. That's 18 over 16. That's 9 over 8. So that's great. I'm done. What about e of y squared? Well, if I just go and plug into the definition for the expected value of a function of a random variable, I'll see that I get the sum over the range of y. I'm summing up the values y squared weighted by the PMF of y. Well, I can plug in the PMF formula. So I'm going to get y from 1 to 6, y squared times 6, choose y, 3/4 the y, 1/4 the 6 minus y. Okay, again, I can do this calculation. It's just 6 terms, but I want to avoid it. I'm always trying to make my life in terms of calculation easier. I don't want to compute this formula out. So is there another way I can do this? Well, if you recall from before, we actually had a different formula for the variance. And you can recognize that it plays a nice role here. So the alternate variance formula we had told us that I can always write the variance as, so I'm just writing this out here, the alternate variance formula. If you remember that formula, it said that I can always write the variance as variance of y is equal to e to the y squared minus the square of e to the y. So all I've done here is just move some terms around, and I see that the second moment, e to the y squared, has to be equal to variance of y plus the square of the mean. Okay, now both of those values are values I can look up in the definition of a binomial. So I plug them in, I get 9/8 plus 6 times 3/4 because it's n times p, and I have to square it because of the alternate variance formula. 9/8 plus 9/2 squared, which is 9/8 plus 81 over 4, which is 171 over 8. And it was nice to avoid a little bit of calculation. Well, finally, what's the probability that I'm watching these 6 matches and the team that I favor wins less than half the matches? And that's kind of sad for me, but that's what I'm interested in knowing. What's the probability that happens? So in this particular case, half is going to be 3 because half of 6 is 3. So what I'm asking is what's the probability that y is less than 3? And again, in this particular example, because I'm only taking these integer values, that's the same as asking what's the probability that y is less than or equal to 2? And in this case, that's going to be y equals 0, summing up from y equals 0 to 2, the PMF of the binomial. So in this case, the PMF of the binomial is just 6 choose y, 3/4 to the y, 1/4 to the 6 minus y. That's going to be 6 choose 0, 3/4 to the 0, 1/4 to the 6th, plus 6 choose 1, 3/4 to the 1, 1/4 to the 5th, plus 6 choose 2, 3/4 to the 2, 1/4 to the 4. If you add all that up, you're going to get 154 over 4,096. Fortunately, there's not much we can do to further simplify this. This was pretty much as simple as it's going to get in this case. Okay, so I had to do a little bit of work to work this out. Okay, and finally, let's ask, okay, given that I know my team is going to win less than half the matches, so I'm going to condition on this event, right? What is the probability that they're going to win exactly 2 matches? So if I just wanted to know the probability that they win exactly 2 matches, that is just plugging 2 into the PMF of the binomial. But in this case, since I have this given statement, I know this is a conditional probability problem. And we actually already have the tools to work out this question, right? So we already know how to define and answer conditional probability questions. So we just need to figure out what our events actually are. So the event we're interested in, exactly 2 matches, is the event A, which is that y equals 2. What we know is that y is less than 3. That's going to be our event B. It's the same as saying y is less than or equal to 2. And the reason for that is that for the binomial, you can only take values 0 up to n. Okay, so we just take those integer values 0 up to n. So less than 3 is the same as less than or equal to 2 in this case. Okay, so the probability of A given B is the probability of A intersect B over the probability of B. Okay, so that's the definition of conditional probability. So I'm going to plug in my event definition. So I have y equals 2 intersect y is less than or equal to 2 divided by the probability that y is less than or equal to 2. And so this works out to be the probability of y equals to 2 over the probability that y is less than or equal to 2. Okay, so on the top, the reason that happened is just that the only thing in common between equals to and less than or equals to 2 is obviously equals to. Okay, so on the top, I'm going to get the PMF value at 2. And on the bottom, I actually know the answer to this. I just worked it out on the previous slide. That was my previous calculation. So on the top, I'm just getting 6 choose 2 times 3/4 to the 2 times 1/4 to the 4. The reason I have that is just plugging into the definition of the binomial PMF. I have to go back a little bit to see that. I keep this fraction on the bottom. If you work out the top, you're going to get 135 over 4,096. Keep the bottom the same. Denominators are going to cancel out. I get 135 over 154. So it's pretty likely that I'll see exactly 2 matches 1 if I know they're going to win less than half.